Okay, thank you for the invitation to give this lecture on the analytic bootstrap in conformal field theory. Um, I think all of you know already quite a lot of things on conformal field theory, thanks to the lectures by Jess. So I'm going to focus on a specific topic, which is the analytically solving conformal field theories by the bootstrap approach. So in 2 dimensions, the conformal algebra is infinite dimensional, and it is the product of 2 Virasoro algebras, left-moving and right-moving. And that makes conformal symmetry particularly powerful in 2 dimensions, much more than in higher dimensions. But still, that's not quite enough for solving any non-trivial theory. To actually exactly solve a CFT, we need more than just conformal symmetry. We need also the existence of degenerate fields. And then this can lead to solutions of CFTs like Liouville theory or minimal models. And that's what I want to explain in this lecture. So the plan is, to start with principles of 2-dimensional CFT. And I think you know already quite a few of these principles, including, what are degenerate fields and what are operator product expansions, OPEs. But here I will review them in the perspective of actually exactly solving the CFTs. And then the technical core of the lecture is to derive analytic formulas for structure constants. So for that, we'll derive, we'll derive BPZ equations and solve BPZ equations. And the solutions we want give rise to single-valued 4-point functions. And from the behavior and properties of these 4-point functions, we can deduce the so-called shift equations for 3-point structure constants. And then we have to solve these shift equations. And this will be done in terms of a special function called Barnes double gamma function. And this gives us a universal result on 3-point structure constants. And then we have to wonder to which conformal field series this result applies. Then I will deal briefly with a few examples, minimal models, Liouville theory, and critical loop models. So are there any questions up to now? Well, don't hesitate to ask questions. But if no questions for the moment, let me start with 1.1. So introduction of some basic principles of conformal field theory and how do we actually solve conformal field theories analytically. So in fact, when a theory is solvable, usually you have several methods for solving it. I will focus on the bootstrap method, but in Liouville theory or minimal models, you can also use the Coulomb-Gass integrals, which follow from the path integral definition of these models. However, I think the bootstrap method, which is based on degenerate fields, is more general and simpler. So how do we solve CFT using degenerate fields? Well, in fact, it's about the same as exploiting conformal symmetry. So if you want to use conformal symmetry to constrain some 3-point function, so let me call it VVV, some 3-point function, then you consider an auxiliary 4-point function, TVVV, where you insert, in addition to your fields, T, which is the energy momentum tensor. Well, we'll do the same with degenerate fields. We also can insert a degenerate field, which I want to call VD12, in addition to my 3 fields. And from the properties of this 4-point function, deduce some constraints on the 3-point functions. So in the case of conformal symmetry of TVVV, the constraints I can derive, well, they are called conformal word identities. And to derive them, I have to know the properties of this T, of this energy momentum tensor, and in particular, its operator product expansions with the other fields. So let me write this operator product expansion in the case of some primary field, V delta of Z, so a primary field of conformal dimension delta. So the indices 1, 2, which appear in VD 1, 2, there will be cat indices, which I will define later, because you have an infinite family of degenerate fields. So back to TV OPE. So this OPE starts with a second order pole, delta over y minus z squared v delta of z. And then there is a derivative term, which is the coefficient of the first order pole, d by dz v delta of z. And then, well, the following terms are regular, and they can be written as follows. The sum from n equals 2 to infinity, y minus z n minus 2, L minus n v delta of z. So second order pole, first order pole, and then regular terms. And in fact, all these terms can be understood in terms of the ln, so the modes of this energy momentum tensor T. So ln, which generate the Virasoro algebra. In particular, the first order pole is d by dz v, which is the same as L minus 1 v delta of z. Well, in fact, that's true for any field, not just for a primary field. And the second order pole is L0 acting on v delta of z, which for primary field is delta times v delta of z. So once you know this operator product expansion, then with the help of the properties of T, in particular the fact that T is holomorphic, d bar T is 0, and the fact that at infinity on the sphere, T of y behaves at infinity as y to the minus 4. So thanks to this property, you can derive word identities for your correlation function VVV. And in particular, these word identities tell you how descendants behave if you already know the correlation functions of primary fields. So in particular, one result which we'll use later is the correlation function of a L minus 2 descendant field. So let's assume I'm considering L minus 2 v delta 1 of z1, all that in a correlation function that involves some other fields, a product from I equals 2 to n of some v delta I as I, all these fields being primary. Then, as I think you have seen in your course, but maybe in different notations, I mean, this is the sum I equals 2 to n of 1 over z1 minus zi, d by dzi, plus delta I over z1 minus zi squared. So this is a big differential operator now, which acts on a product I equals 1 to n v delta I zi. So the meaning of this equation is that if you know this endpoint function of primary fields, which is on the right-hand side, then you can deduce endpoint function of descendant fields on the left-hand side. So what are the questions now? Yeah, I don't see more questions in the chat, but don't hesitate to ask.
Yeah, someone asked, what does the indices 1, 2 signify in like V5, 1, 2?
Yeah. So that the explanation is postponed to a bit later. There are cat indices, which are a particular way to parameterize conformal dimensions, in fact. So yeah, we'll see that a bit later. Well, we'll see that in 2 minutes, in fact. But I'd like to first say a few general things about degenerate fields. So my next topic is indeed So there was section 1.2 degenerate fields. So now we want to do something like that with degenerate fields. So inserting degenerate fields in some correlation function and deducing constraints on that correlation function. But first, what is a degenerate field? So by definition, a degenerate field is a primary field that has a vanishing descendant field. So in general, a primary field does not have any descendant field that vanishes. So because a primary field in general, so let's call it V delta, belongs to some Verma module. By definition, I mean, the Verma module is the representation which you generate by just taking all the descendants of this primary field. And if you wanted to set some of these descendants to 0, then as the representation is irreducible, you would set the whole representation to 0, and everything would become trivial. So, but in special cases, it happens that you can set a descendant field to 0 without setting the whole representation to 0, and then that descendant is called a singular vector. And a singular vector generates submodule of your original Verma module. So it can exist only if your Verma module is in fact reducible. Reducible meaning it has a non-trivial submodule. So then your singular vector, well, obeys Ln. For strictly positive modes, it kills the singular vector. So if you want, that's the definition of your singular vector. Now, let's consider primary field V delta, and does it have any vanishing descendant field? And we could ask this question level by level. So we could look for a level 1 descendant. Well, there is only one level 1 descendant, which is L-1 applied to V delta. The question is whether this is a primary field. And to know that, we have to see if it's killed by the creation modes, by the annihilation modes, by the N with N positive. So in particular, we can compute L1 acting on this L-1 V delta. And to do that, we'll use the Virasoro commutation relations. So here I have an equality because V delta itself is primary, so it's killed by L1. So I can replace L1, L-1 by the commutator. And then using the Virasoro algebra, this commutator is 2L0 V delta, which is 2 delta V delta, since V delta itself is primary with dimension delta. So if you want this to be 0, you need delta itself to be 0. So this tells us that, well, I can have two different types of primary field of dimension 0. So I have V0 itself, so a primary field of dimension 0. So that's just ordinary primary field, and it has a descendant called L-1 V0, which does not vanish. But then if I want this level 1 descendant to vanish, I have to make a special assumption, and then I will change the name of my field. So I will call it now VD11 for a degenerate field with Katz indices 1, 1. And then its descendant at level 1 is 0 by definition. Now, what are the properties of this particular degenerate field? Well, since L-1 means also derivative, it means that the derivative of this VD11 with respect to its position is itself 0. So this field is constant, and we'll see that it's basically the identity field. Well, the identity field is nice, but it won't help us obtain non-trivial constraints on correlation functions. To get non-trivial constraints, we need more complicated degenerate fields. So are there more questions for the moment? Okay, if not, let me introduce some the next more complicated degenerate fields. Well, the next simplest degenerate fields, which are degenerate at level 2 and which are called VD21 and VD12. So, but now to define these fields, I mean, I need new notations. I mean, the VD11 is a bit special because its conformal dimension delta is just 0. It's a very simple conformal dimension, and it doesn't even depend on the central charge. But to write the conformal dimensions of more general primary fields, I need to introduce notations. In particular, the central charge of the Virasoro algebra now will be replaced by a parameter beta. So by C equals 1 minus 6 beta minus beta inverse squared. And then the conformal dimension itself will be replaced by the so-called momentum, by delta equals C minus 1 plus P squared. And now I'm introducing cat indices. So let's define PRS for numbers R and S as the linear combination 1/2 beta R minus beta minus 1 S. So now the statement is that a primary field VP, so now I can, the index of the primary field is no longer the conformal dimension, it is the momentum P. So a primary field VP with P equals PRS. Now, if RS are strictly positive integers, so this VP is a degenerate field in the sense that it will have a singular vector so VP has a singular vector at level RS, R times S, and if this singular vector vanishes, then it becomes a degenerate field VDRS. Now, in the particular case of level 2, in fact, the singular vector itself has a rather simple expression. So L minus 1 squared beta squared L minus 2 applied to VD21 is 0. And L minus 1 squared minus beta minus 2L minus 2 applied to VD12 is 0. So these are the degenerate fields with a vanishing descendant at level 2. And this is pretty much all we need to know about degenerate fields. So I see a question, but I think now you have the answer. The question was whether delta is 0 for VD. Well, it depends on which degenerate field. So delta equals 0 is valid for the degenerate field with a vanishing descendant at level 1. But at higher level, you have a more complicated formula, which is where the relevant delta is given by this formula, basically, the delta corresponding to PRS. Okay, but yeah, sorry, that's on my side. So now the next topic is operator product expansions. Yeah, I see another question. Could the charge be negative? If you mean the central charge, well, the central charge is any complex parameter now. So yeah, I should maybe say that. At the moment, I don't have restrictions on these parameters. The central charge is a complex number. The conformal dimension and the momentum are any complex numbers. And even the cat indices, if you wish, are any complex numbers, except that if I want degenerate fields, I have to take them to be positive integers. Okay, and feel free also to unmute yourself to ask your questions if you want. I mean, I think that would be okay, because I don't always pay too much attention to the chat. Okay, so now, operator product expansions are extremely important because, I mean, they are at the heart of the bootstrap approach to conformal field theory. So the idea of operator product expansion is that if you do a product of two fields, V1, Z1, V2, Z2, you can rewrite it as a linear combination of fields. So let's call Vk the fields in general in my conformal field theory with some index k. And then we'll have some coefficients ck12 of z1, z2. So that's just the basic axiom of CFT that there exist operator product expansions. You can do the product of any fields you want. And if you have these operator product expansions, if you know the coefficient ck12, then you can reduce an endpoint function to a simpler correlation function. You can perform the operator product expansion repeatedly until your correlation function becomes very simple, until it's a trivial two-point function, let's say. So solving the theory amounts basically to determining these coefficients ck12, except that these coefficients are, in principle, well, there are a lot of them because they are indexed by arbitrary fields in your CFT, and they can be complicated. So how do we determine, or at least constrain, these coefficients? Well, the idea is to use crossing symmetry. So crossing symmetry means you can start with, let's say, a 4-point function, V1, V2, V3, V4. And in this 4-point function, you could reduce it to a 3-point function in several different ways. So you could do the product expansion of the first two fields, V1, V2, but you could also do V2, V3. And the result is supposed to be the same. And this equality of results, so this crossing symmetry equation, is a strong constraint on this coefficients ck12. And if you could solve this constraint, you could, in principle, determine these coefficients, except that, well, in the absence of more information or more symmetry, this is impossible because too complicated. So we first should use our symmetries to simplify this operator product expansion. So in particular, we use conformal symmetry. So let me write the operator product expansion in the presence of conformal symmetry. Oops. So let's have V1, Z1, V2, Z2. And the basic idea is that the conformal symmetry determines the contribution of descendant fields from the contributions of primary fields. So it means that instead of having a sum over all fields, as we had before, we'll sum just over primary fields. And then we have some structure constant C1, 2K, but now it doesn't depend on Z1, Z2 anymore. The Z1, Z2 dependence is known explicitly. And let me write it in the following form. So Z12, which is Z1 minus Z2 to the power delta K minus delta 1 minus delta 2. So the conformal dimensions of the relevant fields. And then there's a sum of the descendants. Sum for some L belonging to some curvy L. So I will define this soon. And what do we sum? We sum yet another Z-dependent factor, which is Z to the L absolute value, which means the level of the creation operator L. And then there's a coefficient F delta K L, delta 1, delta 2. All this modulus squared times L L bar Vk of Z2. So now I'm going to describe what this formula means. So the important thing is that L is the set of creation operators, starting with the identity, but also L minus 1, L minus 1 squared, L minus 2, etc. So that the field L L bar Vk is just an arbitrary descendant field, where you have a left-moving descendant L and right-moving creation operator L bar. Then we have these coefficients F, which are known in principle because they are determined by conformal symmetry. So and there is a normalization that the coefficient F for the identity creation mode is just 1. And then there's the modulus squared notation, which just means multiplying something with bars. So if you have some function, let's say g of delta and z, modulus squared, it means you write g of delta and z times g of delta bar z bar. However, there's a difference between delta bar, which is the right moving dimension, and z bar, which is the complex conjugate of z. So delta bar is not necessarily the complex conjugate of delta. Well, it's almost never the complex conjugate of delta, but z bar is always the complex conjugate of z. Okay, so are there questions on this operator product expansion? Okay, yeah. If not, let me write it in a simpler form. So, because the message of this formula is that basically we know everything if we know primaries, because descendants are taken care of by conformal symmetry with these factors f, which we know. So basically, we could write a simplified OP by just writing the primaries. So V1, Z1, V2, Z2, that's a sum over K primary. And we sum C1 to K. So it starts like the above formula, but it will quickly be simpler because I'm just here writing Z12 to the delta K minus delta 1 minus delta 2 squared. And then I have VK of Z2 plus descendants. Now I just write plus descendants because this is something known. We don't need to know the details. Okay, so now let's focus on degenerate fields. So the claim is that the OPs of degenerate fields are particularly simple. So we can start with the simplest degenerate field, which is V1. So V1, which is V11, sorry. So this level 1 degenerate field. So let's take in my OP the first field to be VD11. So this VD11 is constant. So d by dz1 VD11 of z1 is 0. And then this will constrain the OP because this factor z12 to the delta k minus delta 1 minus delta 2 must therefore be z1 independent. And this implies that, well, we already know delta 1 equals 0, so we must have delta k equals delta 2. So the only field which appears, the only primary field which can appear, if I do V1, of V11 with some field V delta 2, well, I must get basically, well, there is a coefficient C122, but then I must get V delta 2 itself. And then you may think I must get descendants as well, but if you look at the descendants come with a prefactor Z12 to the power of the level L. And again, this prefactor must be Z1 independent. And this implies basically that you don't have any descendants in this OP. Yes, so now we have a question about the definition of the product, V1, V2. So we are in an axiomatic approach. So we are not really defining anything. We are just assuming there exists an operator product expansion. This assumption means that whenever I have the product of two fields, I can rewrite it as a linear combination of fields. That's it. There is no definition here. And in principle, this is valid. This axiom could be valid even if you don't have any Lie algebra around. If you don't have conformal symmetry, you could make this type of axioms. And then the second step is that in our case, we do have conformal symmetry, so this OP will take a particular form, constrained by conformal symmetry. So feel free to ask again if this doesn't answer your questions. But meanwhile, I'm coming back to this degenerate field VD11. So we already saw that in its OPE, with some primary field V delta 2, we get V delta 2 itself. We don't get any of its descendants. All we get is a structure constant C122. But in fact, by changing normalizations, you could assume C122 is 1. And this means that VD11 is really the identity. So if you do its product with another field, you just find that field itself. So you can insert it in correlation functions. It doesn't modify anything. Okay, so that's very trivial and in fact not useful degenerate field, because we won't get any non-trivial constraint by just adding the identity in correlation functions. But we will get non-trivial constraints with our next degenerate fields, VD21 and VD12. But first we have to know what their OPEs look like. So if we have VD21 of Z1, let's consider the OPE with primary field VP of Z2 with momentum P. And now I'm not giving you the details, but the idea is that you get only two primary fields which can appear in this OPE with some structure constant C plus minus 1 of P. So there is Z12 to the power plus minus beta P plus 1 minus beta squared over 2, always with the modulus squared. And the two primary fields that appear are, VP plus minus beta over 2 of Z2 plus descendants. So this is the OPE of V21 with an arbitrary primary field. So you may ask, how do I obtain this? Well, in fact, I obtain this exactly like we have just done it for the identity field, except that it's technically more complicated. So for the identity field, we have just imposed the vanishing of the level 1 descendant, which led to this equation that d by dz1 acting on the OPE was 0. Here, of course, it's more complicated, but it's the same idea. The fact that you have this vanishing descendant at level 2 implies constraints on the OPE, and the solution of this constraint is that you can only have two primary fields appearing. And the same story is true for VD12. So if I do VD12 Z1 VP Z2, I also have a sum of some C tilde now plus minus P, then Z12 to the plus minus beta inverse P plus 1 minus beta minus 2 over 2 modulus squared, and then VP plus or minus beta inverse over 2 of Z2 plus descendants. Okay, so these are the OPs of our simple degenerate fields V12 and VP. And in fact, it could be generalized to arbitrary degenerate fields. So if you do VDRS VP, well, I'm not going to write it. It becomes slightly complicated, but the idea is that you get a sum of R times S primaries plus their descendants. And in fact, it's not a coincidence that the number of primaries which appear is the level at which we have a vanishing descendant for this degenerate field. And then, in fact, this gives us, I think, a better characterization, an algebraic characterization of degenerate fields. So instead of defining a degenerate field by the fact that some descendant vanishes, I could define it by the fact that its OPE has a finite number of terms, well, a finite number of primaries. Okay. So this is basically all I have in my general introduction to CFT, or reminders maybe for most of you. And using these concepts, now the task is to actually solve conformal field series by deriving analytic formulas for structure constants. So that's part 2. So analytic formulas for structure constants. So the first topic here is BPZ equations. Now I have a question about C plus minus P. So the OP coefficients in this OPs of degenerate fields, do we know them? And the answer is no, we don't. So at this point, they are unknown structure constants. And there's a good reason why we don't know them. I mean, so far we just impose constraints from symmetry, basically, from Virasoro symmetry, plus the vanishing of degenerate fields. Well, sorry, the vanishing of descendants of degenerate fields. And these constraints are just linear equations, so they can't determine some overall factors. So to determine them, we'll need to do what we are going to do now, so studying some particular 4-point functions. Okay, so now let's remember that these degenerate fields are not really what we're interested in. We just want to use them as auxiliary objects, which we insert in some correlation function to constrain it. So the correlation function we're interested in is a big Z of small zi, which is a 4-point function, which starts with a degenerate field V21 at some point Z0 on the sphere. And then we have 3 arbitrary primary fields, VP1Z1, VP2Z2, VP3Z3. Okay, so we want really to compute this 4-point function. And what we know is that this degenerate field has a vanishing descendant at level 2. Let me write it again. So that was L minus 1 squared minus beta squared L minus 2 VD21 equals 0. So we should insert this equation in our Z, in our big Z here. And basically, we know what happens when we insert L minus 2. That's a formula I wrote already. And we know what happens when I insert L minus 1 squared. That's just a derivative. And therefore, we get a differential equation, which is 1 over beta squared d squared over d z0 squared minus the sum I equals 1 to 3 of 1 over z0 minus zi d by dzi plus delta I over z0 minus zi squared. All this big differential operator applied to big Z of zi must be 0, just by vanishing of this singular vector here. And that's called the BPZ equation, so Belyakov-Zamlodchikov equation. Now, this equation looks a bit scary because it's a partial differential equation in 4 variables, Z0, Z1, Z2, Z3. But in fact, thanks to conformal symmetry, we'll simplify it down to ordinary differential equation in 1 variable. Because by conformal symmetry, essentially, we can reduce our 4-point function to a function of 1 variable, which is the cross ratio Z, which is Z01, Z23 over Z02, Z13. So we have this function big Z of small z, which you can also interpret as the correlation function of VD21 at point Z, VP1 at point 0, VP2 at infinity, and VP3 at 1. So, and this one obeys, I mean, if you translate our partial differential equation into a differential equation for this z of small z, you get an ordinary differential equation. I mean, that's a technical exercise. Well, in fact, you should maybe do this exercise if you haven't done it before. I'm not claiming you can really follow all the calculations in this lecture. So if you really want to understand, it's better to do the exercises after the lecture and do the calculations that I'm skipping, like this one, for example. So if you do this calculation, you should get z minus 1 over beta squared, d squared by dz squared, plus 2z minus 1 d by dz, plus delta 1 over z, plus delta 2 1, minus delta 2, plus delta 3 over 1 minus z, applied to big Z of small z equals 0. So that's just equivalent to the PD above, but that's now an ordinary differential equation. Okay, so now that we have this equation, we need to solve it. Now, does anyone have an idea on how to solve it? Yeah, here I'm actually waiting for some idea. Please, just to see who's following. Or maybe you know the answer. I mean, yeah, Jess, do you think your students already know the answer to that one?
They are shy, I think.
But they know the answer or they don't?
3-point function, they should know, yeah.
Yeah, well, this one is a 4-point function, so it's a bit complicated, right?
Then, oh yeah, I didn't cover 4-point function.
Okay, so okay, maybe you don't know the answer, but that's good. But maybe you have an idea still of on how to solve this type of differential equation. And what's the feature, the main feature of this differential equation? Sorry, I didn't hear you correctly.
Is it a hypergeometric function as a solution or not really?
No, you're right. It will be hypergeometric functions. So it means you know the answer, but the question is how do we get there? How do we find that it's a hypergeometric function? Yes, Hermite function is of the same family as hypergeometric, but okay. I think
is the way to use these singularities at z equal to 0 and z equal to 1?
yes, that's a very good idea. So we can notice that the coefficients, well, especially the coefficient on the right of this equation, they are singular at z equals 0 and z equals 1. And indeed, there is another solution, another suggestion, which says that we should solve them with series. But that's what we do, but we have to decide near which point to expand the solution in series, and we have to do it, in fact, at the singularity z equals 0, z equals 1. When in fact, there is another singularity at z equals infinity, but it's a bit more clumsy to use that. So let's focus on the z equals 0 and z equals 1 singularities. And since there are singularities, we should accept that our solution will have some power-like behavior here, z to the gamma, and then it will be a series. So 1 plus a1z plus a2z squared, etc. So that's one possible ansatz. But then we could have another ansatz based on the singularity at z equals 1, and that will be 1 minus d to the power delta 1 plus a1 plus b1, sorry, 1 minus z plus b2 1 minus z squared, etc. So if you just try a series, it won't work because you have to allow for some non-trivial characteristic exponent, gamma or delta. So these are called characteristic exponent at the singularities. So what happens if you plug such an ansatz in your differential equation? Well, what you find is that the exponents gamma and delta obey polynomial equations of degree 2. So basically, the fact you have a second-order equation in Z leads to a second-order polynomial for gamma and delta. So you have to choose the solution for gamma, let's say, and once you have chosen it, then your differential equation will completely determine all the series expansion. It will determine the coefficients A1, A2, etc. So what are these exponents? Well, if you do the calculation, that's another calculation you could do. Well, you will find plus or minus beta p plus 1 minus beta squared over 2. So that these are the characteristic exponents near z equals 0. So it's BP1 here. And the characteristic exponents near z equals 1, they are plus or minus beta p3 plus 1 minus beta squared over 2. And then you have solutions corresponding to these characteristic exponents. So the solutions with exponents gamma, they are called fs plus minus of z. So that's a solution which starts with z to the power gamma plus minus 1 plus etc. And in terms of operator product expansion, this solution has a simple interpretation. It means that we look at the operator product expansion of V21 with VP1. And if you remember, you had two terms in this operator product expansion corresponding to these two primary fields, P1 plus minus beta over 2. And this solution, F plus, corresponds to taking just VP1 plus beta over 2 and all its descendants. And if you do the sum of all these things in your 3-point function, in your 4-point function, you will find the solution F plus. And if you do it for the primary field P1 minus beta over 2, you'll find the solution F minus. And in fact, these exponents gamma plus minus, they are just delta P1 plus minus beta over 2 minus delta 2, 1 minus delta P1. So the solutions of this BPZ equation are really related to the terms in the operator product expansion. And similarly, the solutions corresponding to characteristic exponents delta near z equals 1, well, they are solutions which I would want to call ft plus minus of z. They start with 1 minus d to the delta plus minus. And these solutions correspond to taking appropriate terms in the OPE V21, VP3. So inside our 4-point function, we can take any OPE we want. So in particular here, the field V21 with VP3. And this OPE was also made of two terms, well, two primary fields here, plus the descendants, which give rise to these two solutions. So in conformal field theory language, these solutions are called conformal blocks. So the Fs plus minus are called S-channel conformal blocks. So let's write again here, S-channel conformal blocks. And there is a standard notation for these things, which is, so that's the degenerate field here on the left. So let me write it like 2, 1, and then field 1, field 2, field 3. So here, this diagram means I have taken the OP of the degenerate field with field 1. And then in the S channel, they propagate a field with dimension P1 plus or minus beta over 2. And the T-channel blocks are represented by this diagram here, where now the field 2,1 has fused with the field 3. In the channel, now you have P3 plus minus beta over 2. So are there questions on these solutions and their interpretation in conformal field theory? Okay, so if no questions, okay. If no questions, let me finish about these BPZ equations, and then we can have a break. So to finish, well, probably I should write these solutions a bit more explicitly, because for now I just said it was a power series you could in principle compute, but what happens if you do compute it? Well, you should find you need a hypergeometric function. So let me just give you, as an example, the formula for Fs plus of Z. So that's Z beta P1 plus 1 minus beta squared over 2. So here you recognize the characteristic exponent. You also have a 1 minus Z to the power beta P3 plus 1 minus beta squared over 2. And then you have times a 2f1 hypergeometric function. So that's a very well-known standard function, well, special function, with 1 half plus beta P1 plus P2 plus P3. So that's the first parameter of this function. This function has 3 parameters and 1 argument. So the second parameter is 1 half plus beta P1 plus P3 minus P2. The third parameter is 1 plus 2 beta P1, and the argument is just Z. So, and the other solutions have similar formulas, but I'm not writing everything explicitly. Now let's think a bit about the space of solutions of the BPZ equation. So it's a second order differential equation, so it should have a space of solutions of dimension 2. And the solutions Fs plus minus, so this is a set of 2 solutions, and that's the basis of the space of solutions. But the Ft also form a basis. It's a T-channel basis. So we have these 2 bases, and therefore there should exist a change of basis, which I can write like that: F epsilon 1 S equals the sum for epsilon 3 equals plus minus of some straight F matrix, F epsilon 1 epsilon 3, Ft epsilon 3. So the Fs and the Ft are functions of Z, but the straight F matrix, which is called the fusing matrix, is not a function of Z. It's just a change of basis. And since we know everything about hypergeometric functions, we also know the explicit expression for this straight F epsilon 1 epsilon 3. And it's built from gamma functions. So you have a gamma function, so Euler gamma function, 2 beta epsilon 1 P1, gamma of minus 2 beta epsilon 3 P3, divided by, well, it's a product here, product of a plus or minus of gamma 1/2 plus beta epsilon 1 P1 plus or minus beta P2 minus beta epsilon 3 P3. So 2 gamma functions in the numerator, 2 in the denominator. So that's really standard. You find that in Wikipedia or wherever you want. And also you can find everything about the gamma function. So that's Euler's gamma function. Euler gamma function. So it's a special function which in particular obeys gamma of x plus 1 is x gamma of x, and gamma of x gamma of 1 minus x is pi over sine pi x. And that's it for BPZ equations. And so our next subject will be to choose which solutions we need for conformal field theory. because we see we have some space of solutions now. But yeah, that's just a mathematical problem. But now we have to look for physically relevant solutions. So are there questions? Okay, so if there are no immediate questions, let's do 10 minutes break. Is that okay for you? Questions for the moment? So are there more questions for the moment? Yeah, if not, the next topic will be single-valued 4-point functions. So one important feature of the correlation functions we want to study in conformal field theory is that they are single-valued. In particular, we saw in some OPEs or even in solutions of BPZ equations, we saw expressions like z to some power delta. But that's not single-valued. That has some monodromy when z moves around the complex plane, unless delta is integer. So to build a single-valued contribution, we should remember that correlation functions, well, they can also depend on z bar, the complex conjugate. So if you have a combination like z to the power delta and z bar to the same power delta, for example, I mean, that's single-valued. That's really a modulus squared, and it doesn't have any monodromy around, around any point. Now, if we want the dependence in z bar, we should say how our fields behave with respect to the right-moving Virasoro algebra, the one which has generators L bar n, and which corresponds to the right-moving energy momentum tensor T bar. And for simplicity here, we'll focus on diagonal CFTs. So a diagonal CFT is a CFT where all fields are diagonals, also all primary fields, sorry. And diagonal means spinless, so the conformal spin is 0, and which means delta equals delta bar. The left-moving and right-moving dimensions are the same. So from now on, when I write a field VP, I mean a field which really has the same left-moving momentum P and right-moving momentum. Okay, so then it means that the right-moving blocks, the right-moving solutions of the BPZ equation will be given by the same expression as the left-moving solutions, just because the right-moving momentums are the same as the left-moving momentums. So we have left-moving solutions Fx, so x means S or T, the channel, with some epsilon of z, and we have to multiply it in order to solve the right-moving BPZ equation with some Fx epsilon bar of z bar. So it's the same f, but with different parameters, and in particular, different argument z bar. So now we have to use linear combinations of this solution. So this product here, f of z bar, this product is the general solution of the left-moving and BPZ and right-moving BPZ equations. But we have to say which linear combinations we consider in terms of we can take combinations by summing over these indices, epsilon, epsilon bar, with some coefficients, d, epsilon, epsilon bar. So we have to determine these coefficients. And we have to do it in such a way that this z doesn't have monodromy. So in particular, around 0, when I do a rotation of 2 pi, I should get the same result. But if you look at our solutions, since they have power-like prefactors, so this f begins with some z to some gamma, well, this means that basically epsilon should be equal epsilon bar. Otherwise, you'll have non-trivial monodromy. And therefore, z, big Z of small z, should be of the type sum of plus minus d plus minus s fs plus minus of z modulus squared. So I only have two terms here out of the four possible terms which I had above, because the terms with epsilon different from epsilon bar are forbidden by this single valuedness condition. And similarly, in the T channel, I should also have two terms with the so-called T channel structure constants, d plus minus t, and then f plus minus t of z squared. Right? Any questions on that? So now, by crossing symmetry, the S channel and T channel expansions should agree. So these two formulas I wrote are just two expressions for the same object, the same quantity. But we saw that S and T channel solutions are just two different bases of solutions of this in the same space. So they are related by this F matrix. So we had an equation like that with F, straight F was the coefficient relating the S channel basis and the T channel basis. And if you plug this change of basis into our expressions for Z in the two channels, it means that the coefficients D plus minus S have to be related to the coefficients D plus minus T. And in fact, the relation is the following. So sum plus minus D plus minus S, straight F plus minus epsilon, straight F plus minus epsilon bar equals delta epsilon epsilon bar d epsilon t. So for any choice of epsilon and epsilon bar. So that's just a change of basis. But now this equation, well, this system of equations, it's a system of four equations for four unknowns. So there are four equations because epsilon epsilon bar take four value. There are four unknowns, which are just the d plus minus s, d plus minus t. So it looks like the only solution must be zero. It's a linear equation, linear system as many equations as unknown. Well, fortunately, in fact, some equations are redundant, so there are only three independent equations, and therefore there exists a non-trivial solution, which means that basically we know the ratios of all these four unknowns. And in particular, we know the ratio of ds plus over ds minus. And you can express this ratio in terms of the matrix elements of the fusing matrix. So f minus plus, f minus minus over f plus plus, f plus minus. I mean, that's a very simple calculation. That's what you get if you solve our linear equations for D. So this determines, in fact, our four-point function, big Z of Z, up to some constant prefactor, some constant factor which doesn't depend on small z. And so, therefore, it determines pretty much uniquely our solution of the BPZ equation. I mean, assuming it is single-valued. No, in fact, we are not really interested in this auxiliary four-point function. We are really interested in constraining three-point functions. So the next topic is to see how this relation, which I just wrote, constrains correlation functions in the CFT. So are there questions? So indeed, let's now see what are these coefficients d plus s and d minus s, the coefficients of the conformal blocks when decomposing our four-point function. So we are in the S-channel decomposition here. So we have the degenerate field 2, 1. We have a field number 1, field 2, field 3. And to obtain this decomposition, based on our four-point function, which was V2, 1, degenerate V1, V2, V3, we did an OP with the field V1, obtaining here some momentum P1 plus or minus beta over 2. Now, when we do this OPE, we have a coefficient which was called C plus minus P1. So this coefficient, if you want, appears when we do the OPE here, C plus minus P1. And after you do this OPE, you get some combination of 3-point functions of the type Vp1 plus minus beta over 2, V2, V3. So therefore, here you will get C, which is a 3-point structure constant. So let me define this notation. So Vp1, Vp2, Vp3 is C, P1, P2, P3, or rather I should write is proportional to C, P1, P2, P3. In fact, you know that due to conformal symmetry, you can completely determine the dependence on Z, so I'm not writing it, the dependence on Z1, Z2, Z3. What matters here is the coefficient, the constant coefficient C, P1, P2, P3. But here, what appears in our 4-point function is P1 plus minus beta over 2, P2, P3. And this product is, in fact, the coefficient small d plus minus S. So, are there questions on this? Because that's a very crucial point. Okay, so if we accept that this is the d plus minus S, it means that our equation, which gives us the ratio of d plus minus S over d minus, d plus S over d minus S, it's a ratio we know in terms of some known F matrix elements. Well, this equation now, giving this ratio, is a constraint for this physical structure constant, C plus minus and CP1, P2, P3. And this constraint essentially tells us how CP1, P2, P3 behaves when P1 is shifted by beta. Now, there is the slightly annoying fact that we still don't know the C plus minus P1. Okay, so these coefficients are not terribly important because they just depend on field number 1. But still, it would be nice to determine them if we really want to determine the general answer for CP1, P2, P3. And to do that, we can consider a special case of our equations by we would focus on a 4-point function of the type V21D, VP, V21D again, VP again. So here we consider a very particular 4-point function with 2 degenerate fields and twice the same primary field. And if you do that, you can show that you get a constraint for just this structure constants C plus minus P. You get more specifically a constraint like this, C plus of P, C minus of P plus beta over 2 over C minus of P, C plus of P minus beta over 2 equals, well, again, something known, some combination of the F matrix elements. So we get a constraint on this C, and the question is, can we determine this C plus minus by solving this constraint? So here I'd like to know what you think. I mean, do we have enough information to determine C plus minus uniquely now? Well, it's just a yes or no question. We could even do a poll. Who thinks it's yes? Who thinks it's no? Ah, right. A brave listener says yes. Yes, up to a phase. So no, we have a slightly weaker guess. But this is closer to the truth, in fact. The point is we still have some freedom because our fields, we are in a bootstrap approach. So we never constructed our fields VP. Our fields VP of Z, they are just defined as some objects obeying some axioms, in particular existence of OPEs. But we can always renormalize these fields by multiplying them with some constant coefficient lambda p. So this is what you could interpret as a phase. And if we do that, we should automatically find another solution, because nothing in what we did so far can fix this lambda p. So indeed, we have a constraint which is non-trivial, but which does not have a unique solution. On the other hand, this means that we can choose the solution we prefer, so as to make the later calculations simpler. And so here, my claim is that to get simpler expressions later, there is a nice solution, which is beta to the plus minus 4 beta p, gamma of minus plus 2 beta p, 2 beta p over gamma of 1 plus minus 2 beta p. Sorry, let me write this 2 a bit more cleanly. And it's not a big surprise that this solution is written in terms of gamma functions, because after all, the known here right-hand side is a bunch of gamma functions. So then, in fact, it's quite clear why this solution makes things simple, because now if I plug this solution in my equation, so if you remember, the equation was giving us the ratio of d minus over d plus. This was just a bunch of F matrix elements which are known and which are all bunches of gamma functions. And now this was also equal to the C plus C over C minus C, but now we know what are C plus and C minus. So therefore we get CP1 plus beta over 2 P2 P3 over C P1 minus beta over 2 P2 P3 equals, well, let me write it explicitly now. It starts with a beta to the 8 beta P1, and then product of 4 factors, 4 gamma factors, which are 1/2 minus beta P1 plus minus beta P2 plus minus beta P3 over gamma of 1/2 plus beta P1 plus minus beta P2 plus minus beta P3. So the nice thing with our choice of C plus minus is that in this equation, I have almost no dependence on P1 alone. I mean, all the gamma factors which only depending on P1 have cancelled, and what remains are the really non-trivial gamma factors which depend on all 3 fields. So this equation, it's an important equation which I would call a shift equation, because it determines how C behaves on the shifts P1 goes to P1 plus beta. And so we got a really non-trivial constraint on a physical 3-point structure constant C P1, P2, P3. And now the question is, can we solve this new constraint? Can we solve this equation? And of course, the first question is, do we have a unique solution? So again, what do you think? Should the solution be unique?
What was the question again?
Yeah, so I have just written a shift equation for the 3-point structure constant here, and the question is the solution unique? Does this equation have a unique solution? And the first answer is, I don't think so, but can someone tell me then why it's not unique, if you claim it's not unique? Well, not much inspiration, it seems. Or maybe you're shy, as Jess was saying. Okay, so a suggestion that it could be cyclical up to a phase. So in a sense, yes, I can always, if you want, I can always multiply C by some lambda C, which, let's say, lambda doesn't depend on anything, but that's a very trivial way to be non-unique. So I can reformulate my question. Is it unique up to this trivial, up to such a trivial phase or prefactor? So maybe I can rephrase again my question. So we have a shift equation which tells you how C behaves under the shift P1 goes to P1 plus beta. So let's assume that it behaved trivially, that it was really periodic with period beta. Would it mean it would have to be constant? Well, no, right? I mean, there exist a lot of periodic functions. Like I could write to you sine pi beta inverse P1, or let's make it even 2 beta inverse pi1, P1. So this function is invariant under this shift P1 goes to P1 plus beta. So even if I find a solution of my shift equation, I can write infinitely many solutions by multiplying with any function of this quantity, sine 2 pi beta inverse P1. So the solution is very non-unique. It's very non-unique because, I mean, to know the behavior of a function under one shift like that is just not very constraining. But I have to remember that, I'm in a CFT, and in the CFT, I didn't use all I could to constrain this function. In particular, we have been considering a 4-point function with V21, but we could also use V12. We could also insert V12 in our 4-point function, in our 3-point function, and then we get the same constraint, but where beta is replaced by beta inverse. So it gives us a shift equation for the behavior on the P1 goes to P1 plus beta inverse. And now this becomes really constraining because the ratio of two solutions has to be a function with two periods, a function which obeys f of P1 equals f of P1 plus beta equals f of P1 plus beta inverse. And are there many such functions? Well, not many, in fact. So if you assume that beta squared is a real number but not rational, let's say, and if you assume that f is continuous, then f has to be constant. And therefore, under these assumptions, our 3-point structure constant C, P1, P2, P3 is unique, modulo just a constant prefactor, which we could say is unique, really. We don't care about this constant prefactor. Okay, so now we have uniqueness, but we still have to find a solution. And so let's stare at our equation again, and we'll remember that we have to solve the same shift equation with beta replaced by beta inverse at the same time. The next question is, how do you find a solution? What type of functions do you need to write a solution? Or maybe I can rephrase this question more precisely. I mean, it's we have a equation with P on the left and gamma functions on the right. So should we look for a solution written in terms of gamma functions? So that's now a question in yes and no. So is the solution a combination of gamma functions? Well, nobody has a guess. Well, the last equation we had was the equation for basically for C plus and C minus, whose right-hand side was also a bunch of gamma functions, and the solution was a bunch of gamma functions. But in fact, I'm trying to mislead you, because here the right-hand side is made of gamma functions, but the solution will not be made from gamma functions. And in fact, we can see it because on the left-hand side, we have P1 plus beta over 2 and P1 minus beta over 2, but that's not what we have on the right-hand side. On the right-hand side, we have a ratio of P1, and then on the denominator, the same function of minus P1. Well, we replace P1 with minus P1. And really, it suggests that the solution will not be built from gamma functions, but it will be built from something else, from Barnes double gamma functions. So that's section 2.4. What we need, in fact, is a function which produces gamma functions when we shift it by beta or by beta inverse. So let me write it like that. Gamma beta of x plus beta over gamma beta of x equals gamma of beta x, and gamma beta of x plus beta inverse over gamma beta of x equals 1 over gamma of beta minus 1x. So here I'm saying we need a function gamma beta with these properties if we want to solve our shift equation. Well, in fact, these properties are pretty much incompatible because using these shift equations, I would have two ways to compute gamma beta of x plus beta inverse over gamma beta of x. Either I do first the shift by beta and then by beta inverse, or I do first the shift by beta inverse and then by beta. But if I compare the results, they don't agree. So to make them agree, I have to slightly modify my equations. Here I need a beta to the beta x minus 1/2, and here a beta to the 1/2 minus beta inverse x. And with this small modification, the equations are compatible. Okay. Now I have a question about sine pi x, but I'm not sure I understand. Maybe that was a question for earlier. So we'll see if there is a more precise question. So for the moment, let me claim that we have two compatible shift equations for some function gamma beta, and the claim is that there exists a special function gamma beta called Barnes double gamma function, which obeys these equations. So yes, the suggestion is to use the fact that gamma of x times gamma of 1 minus x becomes trigonometric, becomes a sine, but in fact, it turns out that this particular property doesn't lead to any simplification in our problem. In fact, we really need the Barnes double gamma function to solve our equation. So now I'm not constructing this Barnes double gamma function because it's pretty much defined by these properties. The solution of these shift equations is pretty much unique, modulo some analyticity assumptions. So the claim is that gamma beta is unique, provided we assume it is meromorphic. So meromorphic in x and also in beta. Meromorphic in x over the whole complex plane and in beta over the complex plane minus the imaginary axis. So this is a special function. It is not as well known as the hypergeometric or gamma function, but still you can find all the properties you need on Wikipedia. And therefore, we can assume this function is known. Probably you don't know it yet, but it's only a matter of looking up what are its properties. And therefore, I can use this function to solve the shift equations. And the solution is C P1, P2, P3 equals product over 3 independent signs plus minus plus minus plus minus gamma beta inverse, meaning the function 1 over the function gamma beta of beta plus beta inverse over 2 plus minus P1 plus minus P2 plus minus P3. And this is really a good solution for a 3-point function because it is permutation symmetric. I mean, you can permute P1, P2, and P3 without changing it. And you can check, based on the equation we have so far, that it solves the shift equations, not only in beta, but in beta inverse. Well, in fact, it's quite clear because it's invariant on the beta goes to beta inverse. So if it solves one equation, it will solve the other as well. And that's, let's say, the technical result of this lecture. So the technical result is we have seen, based on a few assumptions, how to derive this 3-point function. And the next question will be, in which CFT is it relevant? I mean, which CFT are described by this result? So are there questions?
Yes, there are not another factor in front that is not fixed, or is that number the structure, this 3-point function?
So you want to know if I can put a constant prefactor?
Yes, if you determine all the 3-point function, or you have another degree of freedom that you are not fixing with this.
No, so there is still the freedom to renormalize the fields, right? There is this VP of Z goes to lambda P VP of Z. So when we chose the particular value of C plus minus P, we fixed this freedom, but we could still do a renormalization, and this would modify this function. And then there's also the freedom C goes to lambda C, where lambda is constant and doesn't depend on P1, P2, P3. So up to this, yeah, so that's the only freedom you have.
Okay, so in the OP you get this number in particular, or in the OP of the in the 3-point function of the 3 primary fields, get this number and the dependence on the coordinates.
Yeah, I just have these freedoms.
Okay, thank you.
Okay, you're welcome. Oops. So let's apply this to some CFTs. So which type of CFTs could we potentially solve? Well, we made the assumption of diagonality. So we want all the primaries to have the same left and right dimensions. So of course, we won't solve the CFTs that are not diagonal. So let's start with minimal models. Well, some minimal models are diagonal and some not. So let's review that quickly. So what is a minimal model? So I think you have already heard about minimal models, but now I want to define them well as CFTs with a finite numbers of primary fields. Well, that's probably the definition you know, if you know any definition. So you can classify the corresponding torus partition functions by solving modular invariants. So if you want, modular invariance equations are analogous to conformal to crossing symmetry equations, but they are technically simpler. So if you solve modular invariants, assuming you have a finite number of primary fields, you find a classification of conformal field series of minimal models. It's an AD classification. meaning you have three series, A series, D series, E series. It doesn't really show that these minimal models exist, because just having a modular invariant partition function is not a sufficient condition for a CFT to be consistent. But in this case, they exist. But now, what do they look like? So let's forget about partition functions. So I'm not getting into these technical details, but let's think more about degenerate fields, because by definition, we want a finite number of primaries. So it means that when we do an OPE, we should have a finite combination of primaries. And this implies that all the fields should be degenerate, because, well, that's pretty much the definition I gave of a degenerate field. The fields whose OPs are finite, well, in terms of numbers of primary fields. But in fact, it's not enough for all fields to be degenerate, because let's say I start with V21 and I start taking OPEs. So let's say V21, V21, then I will get V11, V31. But then I can continue to do multiple OPEs. So V21, VR1, let's say, for any integer R, I'll find, well, a sum of two terms, VR minus 1, 1, VR plus 1, 1. And if I do it recursively, I'll obtain all the VR1 with R integer. And therefore, I'll get an infinite spectrum, an infinite set of primary fields, even if in each OPE, there is only a finite set. So clearly, that's not sufficient to build a minimal model. I need the OPs to be even more constrained. And to do that, I need fields to be doubly degenerate. So let's have a VDRS, but let's assume it's also degenerate at some other level, R prime S prime, and therefore its OPs have to obey both the constraints from this vanishing singular vector and from this vanishing singular vector. That starts to be a lot of constraints, and in fact, it will make or it will lead to a minimal model. But it immediately implies that you cannot have minimal models at arbitrary central charge, because if these two fields are equal, it means in particular that they have the same conformal dimension. And so it means in particular PRS is plus or minus PR prime S prime. So that was equivalent to delta RS equals delta R prime S prime. And if you remember that PRS is just 1/2 beta R minus beta inverse S, and if you have this equality PRS equals plus or minus PR prime S prime with RS R prime S prime integers, it implies that beta squared has to be rational. So minimal models can exist only at rational beta squared and therefore at rational central charge. In fact, not only rational, but it turns out if you want a minimal model, you need beta squared. Oops. Beta squared equals Q over P should be strictly positive and not negative. And then the spectrum of your model is given by the Katz table. The Katz table, which is a set of degenerate fields, VDRS, where R is an integer going from 1 to P minus 1, and S goes from 1 to Q minus 1. So that's indeed a finite set. The claim is that it is stable on the operator product expansions, and therefore the spectrum of minimal models should be built from primary fields of this type. Now, I've just said it for the left dimensions, but the same story is true for the right dimensions, but I still didn't say how to couple the left and the right. In principle, we could have primary fields with different indices on the left and on the right, R bar, S bar. And that's where the three series come. So the A series is diagonal with RS equals R bar, S bar. And the D and E series are non-diagonal, which means that for some fields, RS is different from R bar, S bar. So, are there questions on these minimal models? I mean, do you recognize the minimal models you know already?
So only for the diagonal, we have this result that the 3-point function is this number.
Yeah, right. So I'm going to give the result for the A series. The other series are more complicated, and in fact, I would say the E series is not completely solved yet. We don't really know explicitly the 3-point functions. But now, yeah, the claim is that for the A series, all I have said, I mean, starting from BPZ equations, etc., all that is valid for the A series. And therefore, our formula we had for 3-point functions should work for the A series.
Okay, so we also know all the primaries that appear in the OPE, for example, of the two first primary fields in the 3-point function, for example, no? With this information, you know.
Yeah, we know the OPs because they are dictated by the null vectors, basically, by the singular vectors.
Okay. In the D and E series, it's more complicated. It's more difficult to know which are the operators that appear in the OP. You have more constraints or something like that, no?
Yeah, that's the problem, yeah.
Okay.
But in principle, you can use the same methods in the D and E series. It's just technically more complicated. And in the D series, you can still do it systematically, but in the E series, it's hard to do it for all cases. It's like you could apply these methods to any 4-point function you're interested in, but if you really want to compute all 4-point functions, it becomes very complicated. Okay, so now let's go back to the A series because that's what we are interested in now. And in this case, indeed, our formulas should apply. So the formula I wrote for CP1, P2, P3 should be valid for the A series, except that this formula does not have the normalization which is usually present in A series. In particular, in A series, we want VD11 to be the identity. And as we saw before, there is a question of normalization. I mean, we really want it to be the identity, 1, and not some number when multiplied with another field. And also, we would like the 2-point functions to be trivial. VDRS, we would like it to be 1 and not some other number. And so the solution we have for CP1, P2, P3 does not have these properties. In particular, well, if you compute CP11 and then some PRS. So let's call C tilde the 3-point function of A series minimal models, but correctly normalized. So our assumptions about the identity about 2-point function just essentially mean that the C tilde P11, PRS, this should be 1. But if you compute it from the formula we have for CP1, P2, P3, it's not 1. But we can make it 1 by using the freedoms we discussed before. I mean, the freedom to renormalize fields. So in this case, VRS, we can renormalize it with some coefficient RS. And then the freedom to renormalize C by some overall constant coefficient. And then the correct normalization, which gives you the desired properties, is the following C tilde. So C tilde should be, well, of course, it should be CP1, CPR1, S1, PR2, S2, PR3, S3. But then you have these normalization factors, which are square root of CP11, P11, P11 over product I equals 1 to 3, CP11, PRS, PRS. So the claim is that this combination obeys the assumptions about the identity and about 2-point functions. And therefore, this is the solution of A series minimal models. Okay, so the nice thing about this solution is that it's general. It gives you all 3-point functions in all A-series minimal models. Well, the less nice property is that it's complicated, right? It's written in terms of this Barnes double gamma function, and not only this, but you have a whole bunch of such functions. So if you want to study a specific minimal model, typically you will have to evaluate all this, and there will be simplifications. So for example, at c equals 1/2, you have a minimal model related to the Ising model. So I would say it describes some fields in the Ising model. So that's beta squared equals 3/4. And there's only one non-trivial 3-point function in this model, which is called sigma epsilon, which in our notations, it would be C 21, 21, 31. And if you compute all this bunch of double gamma functions, but then you use the properties of the double gamma function, the fact it reduces to gamma functions and the shift equations, and gamma functions themselves, they can be simplified. And eventually, what do you find? I mean, which number do you find? Does anyone know that? Well, you're not expected to be able to do the calculation in 10 seconds, but the answer is 1/2. But that's a bit specific to this particular model. So in a general minimal model, if you do all the simplifications you won't end up with such a nice rational number. Typically, you will end up with a bunch of gamma functions. I mean, you can always eliminate all the double gamma functions, but you'll be eventually stuck with gamma functions. Okay, so that's all I want to say on minimal models. Are there questions? Oops. So the next example is Liouville theory. So Liouville theory now, in contrast to minimal models, exists for any complex value of the central charge. And we can define it as a diagonal CFT whose spectrum, whose primary fields are VP, P belongs to R plus. So, well, it's R plus because, I mean, I couldn't take the real numbers because I have VP equals V minus P. So if I want to have just one primary field for each dimension, for each real dimension, basically I need R plus here. And then the big subtlety, I mean, is, okay, all I have said before, all this result about CP1, P2, P3 relies on the existence of degenerate fields. But here I'm writing a spectrum that does not include any degenerate field. So how can I use the previous result? And the answer is that we assume that degenerate fields exist. But they are not part of the spectrum. Which means, if you want, that you can always compute a correlation function which involves degenerate fields. But if you do any OPE, like VP1, VP2, you will not find any degenerate fields. In fact, you will just find the integral. You will just find all the other fields, VP, but you will not find any degenerate fields. So the theory is consistent without degenerate fields, but you can consistently add degenerate fields. And therefore, you can apply the constraints that you get by the study of VD21, VP1, VP2, VP3, as we did. And this constraint essentially fixes for you CP1, P2, P3. It's the formula I wrote before. And this shows that Liouville theory is unique because essentially we had a unique solution for CP1, P2, P3 up to some normalizations. And now that's the only solution, the only possibility for Liouville theory, modulo our assumptions. Now, there are big subtleties about the values of the central charge and the analyticity of structure constants, because this unique solution I wrote is valid only for C less than 1. And you can analytically continue the 3-point function to complex values of C, but you cannot continue the 4-point function. That's because of subtle analytic properties of conformal blocks. If you want to have more general complex values of C, and in fact, if you want C to be any number in the complex plane except this half line, you need another solution of the same shift equations. And this other solution is called the DOZZ formula for Dorn-Otto, Zamolodchikov, Zamolodchikov. And it's also written in terms of the double gamma function, but it's a slightly different combination. So here I'm introducing a small b, and it's a gamma b, b plus b inverse over 2 plus minus IP1 plus minus IP2 plus minus IP3 over product I equals 1 to 3 of gamma b of 2 IPK. Sorry, it's a k here, the index, and gamma b of b plus b inverse minus 2 IPK. And b, by definition, is I beta. So to write this DOZZ formula, I've taken the solution I had before, but I've put some i's in the parameters of the gamma of the double gamma function, some i's also in the variable, in the argument, and then the double gamma function, which depends on the 3 momentums, are now in the numerator instead of the denominator. And on top of that, I've adopted a different field normalization. I have this denominator here, which is basically obtained by changing field normalizations. And this particular normalization emerges from a path integral calculation, because Liouville theory was originally derived, constructed by a path integral, and the solution derived by Dorn-Otto, Zamolodchikov in the 1990s, is obtained by doing calculations. So in this path integral formalism, the fields are constructed, and you don't have any freedom to change normalization, so you get a specific normalization here. Okay, so that's Liouville theory, and the last subject will be loop models. But are there any questions? Okay, so now we have the same formula, CP1, P2, P3. It was also found to describe some 3-point functions in critical loop models. So what are critical loop models? Well, in critical loop models, obviously you have diagonal fields, VP. Otherwise, our formula wouldn't mean anything in this model. But it's not all. In addition to these fields, you have in the spectrum some non-diagonal fields, fields with momentums, left and right momentums, PRS and PR minus S, so a priori different left and right momentums, where now the indices, they are Katz indices, but they are no longer integer. The first index can be a half integer, and the second index can be fractional. Now, since we find that we have the same structure constant, CP1, P2, P3, as in Liouville theory, well, some people have thought that maybe loop models are closely related to Liouville theory. Maybe loop models are some extension of Liouville theory. But in fact, that's completely wrong. I mean, the reason we have the same formula CP1, P2, P3 is just because this formula is the solution of some universal problem. And it follows from our assumptions, basically, from crossing symmetry, degenerate fields, etc. So the fact you find the same formula in various CFTs, that does not mean that these CFTs are directly related. And in fact, in critical loop models, the OPEs are very different from what you have in Liouville series. So in Liouville series, as I showed above, your OP of two fields was just VP1, VP2 is an integral over fields VP. But in in critical loop models, the OPE, VP1, VP2 is not an integral. Oops, it's just a discrete sum. Which discrete sum? Well, in fact, you have an infinite series of diagonal fields of the type P0 plus K beta inverse. And then you have a sum over the non-diagonal spectrum, except the first index now is integer. So sum for R integer S in 1 over RZ of VRS. So this OP just shows it's a very, very different CFT, but the same formula for CP1, P2, P3 is valid. Now, the real puzzle is why CP1, P2, P3 appears. Because in critical loop models, we have the degenerate field V12, but we certainly don't have V21. We cannot add V21 to the spectrum of the model because otherwise, this field would shift the first Katz index by 2, and this wouldn't be compatible with the values of R and S, which we have assumed here. In particular, if you shift R by 2, the condition that S is in 1 over RZ is broken. So it's still an open question why this CP1, P2, P3 is relevant to critical loop models. Yeah, and that concludes this lecture.